that was a really great introduction. It is what I work on, but today I'm going to talk to you guys about a little pet project that I had instead. And these sometimes come up, and sometimes you can ignore them, but sometimes it's better just to go along with it. I was going through the research, looking at something entirely different, and essentially I came across a mention of this dredge function. And I didn't think much about it at the time. I was like, oh, kind of interesting. I haven't seen this package before, but okay, sure, whatever. But as time went on, I kept seeing it again and again and again and again. And so at this point in time, I decided, okay, I really want to look into this. This is relevant to the research that I've been working on, so what is going on? So the dredge function is actually an automated model selection tool, or sometimes more colloquially known as a tool to engage in data dredging. So for those of you who are not as familiar with automated model selection or data dredging, essentially it's a tool used to extensively search and compare different model configurations using the same data set. So for example, imagine you have this global model here. This is the terminology that we like to use. So this is a global model, and this is what gets put into the dredge function. And so when you put in a model like this that has 4 different variables, this is what dredge does. So it creates all different combinations of these models, and it generates them, compares them, and gives you an output of a table saying which one is best and which one is not. Okay, so you can start to think, well, we put in 4 variables there, and we got 16 model combinations. What happens if we adjust the number of variables that we're going to put in? So on here, on your x-axis, you have your number of predictors, or essentially those number of variables that you put in. And on the y-axis, you have the number of candidate models, so all the different model configurations. So there's the one with 4, it's got 16, and you can see it right at the bottom. Well, as you increase the number of variables in there, it's starting to get a bit bigger. Okay, but if you know anything about math, then you might start to think, well, this is exponential. So that means that while 16 models is still quite a few when using 4, by the time that you actually get to inputting a model with 10 predictors, which is something that we see quite often, you're ending up creating over 1,000 different models that you're actually comparing and testing with one another. And if you're adding interactions, so a multiplicative effect, this number is even larger. So there you can see with 1 and 2 interactions. And originally when I was seeing this, I was like, okay, data dredging, it's kind of a bad term that we use it, but it's an automated model selection tool. Maybe this is just being used only in exploratory research or only in predictive research. Well, in fact, this is not actually the case, because I was seeing them in papers that were actually based on testing hypotheses or evaluating different hypotheses. So at this point in time, I was very much intrigued, and so we decided to write a paper, as you do. And so the main objectives really first were whether data dredging, or specifically the use of the dredge function, is becoming more common. So this was all anecdotal. I was seeing it pop up. I hadn't seen it before. But is it, in fact, actually increasing? Now, we couldn't look across every single discipline out there, so we focused it specifically on ecology, as this was many of the journals that I had first seen this dredge function pop up. And if this is the case, that it actually is increasing, then we can ask, well, what are its potential consequences when we're doing research in inference, exploration, and prediction? Okay, so let's focus on this first one. So what we did first is we conducted a really basic survey of the literature. So we pulled every article that mentioned dredge, and specifically dredge from the Human package, and any version of ecology, so ecological, ecology, etc. And then we went through all these different articles and checked if they were exploration, hypothesis, or prediction driven, or unspecified. And we plotted these trends over time. So this is what we ended up getting. So really, we found that the number of articles using dredge has been increasing over time. And if you look to 2024, it's actually over 600 articles, new articles that year. And another thing you may notice looking at this figure is this increase applies to research with different modeling objectives. So here the blue is hypothesis driven, which was the most common, and you can see that increase more pronounced. But we actually also saw it with prediction and exploratory driven and even this unspecified. So it is continuously increasing over time. And it wasn't just limited to a single journal. As I said, I was going across the literature and it was popping up in all these different places. And so in surveying it, again, just with the limitation of ecology, we saw all of these different journals that were actually using this function. Okay, so is it becoming more common? Well, yeah, I think in our basic survey, it's an underestimate and we see that it's increasing, so yes. So now on to our second question. Well, what are its potential consequences? Now this is a bit harder to try and figure out. So to do this, we actually picked a case study and nothing to do with ecology, nothing to do with infectious diseases. We decided to have fun. And this is an open data source that you can find online. So it's with NASA and a partnership of another group. And this is looking at meteorite mass. So on the website, you can find the number of meteorite landings, the meteorite mass, as well as the geographic coordinates for where they all landed on Earth. And so we decided to use Dredge to assess the performance using this particular case study. And so what we want to do is apply the Dredge function to models of meteorite mass using climate and land cover variables as predictors. And the reason why we picked land cover and climate is because we really didn't think it had anything to do with meteorite mass, so like this is a perfect test to assess this. And so you guys probably are somewhat familiar with these variables. So world clim, you see it pop up everywhere. These are averages looking at temperature and precipitation primarily. And then we used modest land cover. We just picked one land cover type, so shrub class is what we used. And so what we want to do is evaluate the performance of the top ranked models according to Dredge, which are those with the lowest AIC scores, with lower ranked models according to AIC. So just as a fun reminder, I'm sure many of you have used AIC or come across AIC before, but it contains two main components. So the first one is the log likelihood. So this is really your model fit. How well does the model actually fit your data? And the second part is a penalty. So here it's 2 times the number of parameters that you actually have in your model, your number of terms. And as I mentioned, we want to compare these top ranked models with the lowest AIC with lower ranked ones. And so our lower ranked models were twofold. So the first was the best performing by AIC that were not the top ranked models by different model sizes. And then the second one was median performing models by model size. And by model size, again, what I mean is the number of terms, essentially, or number of variables that are in our model. And there you can see it's LMER, and this is just because we were using mixed models rather than just a linear model. And so to evaluate the performance of these, we did it twofold. So first, for the hypothesis and exploratory driven, we used in-sample performance. And so what this means is that we actually assessed these models using data that was involved in the model fitting. So 1970 to 2000, we fit the data and then we assessed the in-sample performance using that same data. And here we did a marginal R-squared. So for those of you that are familiar with mixed models, so your marginal R-squared is just the variance explained by your fixed effects, so really the variables of interest. And then to look at our prediction-driven performance, we want to do out of sample. So here we evaluated the models using withheld data, so our 2001 withheld data, and we used a mean absolute error. So just a measurement of the error between our prediction and the actual outcome. Okay, and so here is the global model that we ended up putting in. You can see the world clim and you can see our modest land cover. And on top of it, you may notice that we also have 2 interactions. Now, we wanted to make sure that these interactions were not cherry-picked. And so essentially we did every single combination of the interactions and reran Dredge over and over and over again. So really, we reran the Dredge function 210 times to capture all possible pairwise interactions. Okay, so what were our results? So first of all, again, we ran it 210 times, putting that global model with different interactions in Dredge over and over and over again. Dredge tended to pick larger models. So here on your x-axis, we have the number of top-ranked models, and on the y, you have the model size. So first of all, you may notice there is no model below 6 terms that was selected as a top-ranked model. 9 predictors was the most common, and you can actually see that interactions were commonly included. So long story short, what this is saying is that the dredge function tended to pick more complex models than simpler models. Okay, so now let's look at this model performance for this exploratory and hypothesis-driven context. So again, we have model size just on the bottom, and here we have that marginal R-squared, so that explained variation of our fixed effects. Okay, so there's those top-ranked models. Remember, I said there was none less than 6, so you can see everything there. And on average, you're looking about 28% of the variation explained. It's all right, model. It's okay. Now here is the high-performing models that were not the top-ranked overall. Now, one thing I want you to notice right away is that the R-squared of the dredge-selected models was less than 1% higher compared to a lower-ranked 5-variable model. So if you look at 5, the difference between them is very, very small when it comes to the explained variation. What about the mid-performing? So we see a bigger difference, but I still want to point out that by the time that we get to about 5, 6 terms in your model, you're actually not getting that much of a difference. So for example, a model there with 6 that's mid-performing only explains about 3% less, so 25%, compared to adding 4 additional variables to actually explain more in our top-ranked models. And when we look at the AIC, because we know this is what it's being judged on, we can actually see that there are large differences. So just as a reminder, a delta AIC of greater than 2, we determine usually to be a meaningful difference between the fit of these models. And so remember, I said, with your mid-performing model of size 6 is only 3% difference in variation, but you're looking at an AIC difference of 500. So this is huge. And really what this should start bringing up in your head is maybe this extra fit and everything is probably due to overfitting. It's not just that this is real and meaningful. And this can happen particularly when you're dealing with really large data sets. Very small improvements in fit can translate to very large differences in AIC. But maybe now you're sitting there and being like, okay, causal. Like this is overfitting and causal, but maybe it's really good for prediction because AIC actually is supposed to be a measure of prediction capacity. And I would say, great, you guys have been paying attention in your stats classes. Fantastic. Okay, so let's see, how does it do then when it comes to prediction? Okay, so again, we have our model size on the bottom, and then we look at our mean absolute error, this time on our y-axis. And just to reorient you now, lower is better. So we want lower error. So what do we get? So long story short, we're not actually seeing any difference in predictive performance here. Doesn't matter mid-tier, doesn't matter our top performing, doesn't matter model size, anything. And just to let you know, these are all bad predictive models. I just want to tell you guys that. None of them are good, and none of them are actually really better than any other one. So what are our key takeaways overall from this study? Well, 1, Dredge consistently favored more complex models, often those with 8 to 10 parameters. 2nd, for our in-sample assessment, so really looking at that assessment of our exploratory and hypothesis-driven models, top-ranked models did not substantially outperform the simpler, lower-ranked models. And this is a question of what is better, and that is something that we could debate for hours, but we didn't see large, substantial differences. And finally, for out-of-sample assessment, looking at our prediction, our top-ranked models exhibited overall, like I said, low predictive performance, and they were not any better than most alternative models. So what are its potential consequences for inference, exploration, and prediction? Well, data dredging, or let me be more specific, the dredge function, can result in selected models that are not optimized for inference, exploration, or even prediction. And in fact, this shouldn't entirely be new, because when you go to the package itself, it has this wonderful quote in there that users should keep in mind the hazards that a thoughtless approach of evaluating all possible models poses. Although this procedure in certain cases is useful and justified, it may result in selecting a spurious best model due to the model selection bias. And often in these papers, they also quote Burnham and Anderson, who is our AIC gods that we have. And in fact, they also actually warned about comparing too many models, not just through using something like Dredge, but just in general, that if we have many, many models and we're comparing them, you have to be extremely careful. And so, in that is the end of my presentation. Short but sweet, but also I could not do any of this without my funding support. So that is all.